6.2. Now we've already done some of the material out of 6.2. We've looked at the portion of 6.2 where we have we had U substitutions that involve some clever trig identities is the word I'm looking for. Some clever trig identities and some clever U substitutions and saying, okay, do we have even powers on cosine or sine? Do we have odd powers on cosine or sine? And then working with those. There's another technique in section 6.2 that's called trig substitutions. Now, even though the other trig stuff that we did in 6.2 involved U substitutions, this is kind of an entirely different animal. All right, so some things to remember, and that are going to be really useful for today, are that sine squared theta plus cosine squared theta is equal to 1. So hopefully you all have made your appointment to have your tattoo done, have that written on your arm. The other one that we're interested in is tangent squared theta plus 1 is equal to secant squared theta. And those two identities are going to play a huge role in today's lesson. All right, so these two identities you want to remember. And trig substitutions are useful for integrals that involve forms such as the square root of a squared minus x squared, the square root of x squared minus a squared, and the square root of x squared plus a squared. So when we have integrals that involve a number squared minus a variable squared or some form of that under a square root, these trig substitutions might be the way to go. Now, not 100% of the time. I mean, we already know how to solve some integrals that involve those square roots. For example, we can already solve some like this. For example, the integral of 2x over the square root of 4 minus x squared dx. When I look at this integral, I see a square root and a number minus x squared, so that falls into this first form right here, where the a is 2 in this case. 4 is 2 squared. So that falls under this form, but we already know how to solve an integral like this, something like this integral. Take a look at it and think about how you might go about evaluating this integral. And then turn to your neighbor and tell them what you think.
What you say? Are you going to do this one?
Okay, so stop wherever you're at. Even if you're working through the whole problem in your head or on your paper, all I want to know about is what is your first strategy, or first step in your strategy?
Change and eradicate to a 1.5.
Pull the 2 out, then multiply to clean the fraction out, take x and make it a product of 1 over, so then you've got by parts looking at you in the face there, and a clean fraction that's 1 over that root.
I'm not following what you're saying.
So to take the 2 out,
Okay.
and then you're left with x over that. So then do x times 1 over.
So x times 1 over 4 minus x squared dx, I guess.
So would that technically now clean the fraction up enough to start working that, and then you've got a product there, so you know you've got a by parts situation with that x times that fraction.
Okay, so one option here is that we might be able to work with a integration by parts. Now, certainly with integration by parts, what I see here is two separate algebra values. And so the next question would be, what would I choose for my u? And you could mess around with that and keep working with that. So integration by parts, I would have to choose a u, and I might have to play around with it a little bit because both of these pieces are algebra pieces in terms of that acronym, the LIATE. Okay, so this is one way to go about this problem. Other ways.
I would just sub the 4 minus x squared as a u, and then just have it as 2x times u to the negative 1/2. And once you do all the u sub stuff, that 2x is just going to go away. And you have a u to the negative 1/2 to integrate.
Alright, so another option is 2x over 4 minus x squared dx. And so do a u sub, and choose u to be 4 minus x squared. Okay, our derivative would end up being negative 2x, and so that's going to help cancel our 2x in the numerator up there. Okay, and then we could clean that up as well. Okay, so we have two possible strategies. Okay. So good ideas, both of them. Over here you may have to mess around and determine which of these two you want to be your u, and then work from there. Okay? But I believe that both of these will end up working in the end. So we can already solve some indefinite integrals that involve these forms, these square roots. All right, but there are others that we don't know about. So what I'm going to do here is I'm going to erase this even though I just wrote it down, so if you still need it, anybody still need this up here? Okay, I'm going to set up a table over here, and we're going to fill in this table as this hour moves forward. We're going to look at 3 examples of trig substitutions. And so we're going to start the table by looking and listing the form. And so the first form that we're going to look at is square root of x squared minus a squared. And just so that you have your notes enough space, we're going to have 4 columns. Our second column is going to be the identify with column. The third column will be the substitution. And the final column will be the result. So you'll need 4 columns. Okay. Here's our first example. We have the integral of 1 over x squared times the square root of 9 minus x squared dx. Okay, so this is an example where we have a squared minus x squared. So this is our square root of 3 squared minus x squared is our first form that we see here. Now, in terms of maybe trying to do a u substitution, I'm not going to be able to do that. I'm not going to be able to cancel this extra x squared that's in the denominator here. Okay, so here's how the idea of a trig substitution works. We would like to be able to manipulate and mold this fraction in here so that the square root can be simplified. Now, it's totally illegal algebra to split up the square root over the 9 and the x squared. Never allowed to do that because we have subtraction in there. Okay? So what we need to do is we need to be able to rewrite this 9 minus x squared as one term so that we can actually take the square root of it. Okay, so what I want to write down over here is those 2 identities that we had. Sine squared theta plus cosine squared theta equals 1. And tangent squared theta plus 1 is equal to secant squared theta. Alright. Now what I'm thinking about here is this part under the fraction. I'm looking at the 9 minus x squared. And from this 9 minus x squared, I see a number and I see a variable squared. And right now you're saying, what the heck does this have to do with these trig functions up above? When I look at these trig functions up above, like to be able to write one of these trig functions as a number minus one of those trig functions squared. Now there's a couple of different ways that I can do this, and the way that I'm going to choose to do this is that I'm going to rewrite this first one. 1 minus sine squared theta is equal to cosine squared theta. And so what I'm trying to identify here is that I've got a number minus a variable squared, and I've got a trig identity where I've got a number minus a trig function squared. All right, so this is the connection that a mathematician quite a while back came up with and said, okay, this is kind of cool. They kind of look similar to each other, but this has a 1, and I really want a 9. So in order to get a 9 here, I'd have to multiply everything by 9. So I could rewrite this as 9 minus 9 sine squared theta is equal to 9 times cosine squared theta. All right, so keep watching this and see what's happening here. I want to manipulate my trig identity so that our left-hand side looks like 9 minus something squared. So over here, I've got 9 minus. Now, 9 sine squared theta, I could rewrite that as 3 times the sine of theta, the whole thing squared. And I can do the same thing over on the right-hand side as well. 3 cosine theta, the whole expression squared. Okay, so I'm doing a little mathematical magic here, and it's not really clear why I'm doing this, but we're going to see now why this is useful. This expression that I have written down here looks like 9 minus stuff squared, which looks an awful lot like this expression up here, 9 minus stuff squared. So if I make a substitution where I say let's let x be equal to 3 times the sine of theta, let's see what happens to our integral. All right, so we want to transform this integral. Now we've got the integral of 1 over x squared times the square root of 9 minus x squared. Well, what is x? X is 3 sine theta, quantity squared. And then we've got a dx at the end. Okay, so I just made this one substitution. Now, like a u substitution, we cannot have x's and another variable all mixed together. So we've got to turn our entire integral into thetas. So some things that will have to happen. This dx at the end is going to have to be a d theta. Right now we know that x is equal to 3 sine theta. So since x is equal to 3 sine theta, then dx over d theta is equal to 3 times the cosine of theta. And so dx is equal to 3 cosine theta d theta. Okay, so we can write this as 1 over x squared times the square root of 9 minus 3 sine theta squared. And our dx is 3 cosine theta d theta. All right, now at this point you're saying, Diane, you must be going nuts up here because this looks way worse than it did in the very beginning. Okay, so I look back at this and I say, okay, do I see any more x's up here? And the answer is yes, I see an x squared right up here. So I've got to replace that And I know that x is equal to 3 sine of theta, so I can write that in here and square it. So we've got the integral of 1 over 3 sine theta squared times the square root of 9 minus 3 sine theta squared. And then my d theta was 3 cosine theta d theta. Okay. I have now turned my entire integral into thetas, and it looks awful. Are there any questions about turning this all into thetas? Okay, so why would I possibly do this? Why would I want to do this?
To make it easier for the, I'm guessing, the u substitution step that's going to follow?
Okay, so it is going to make our life easier. So that's a possibility, but I'm not actually even going to go there. So before that, yes?
Well, under the square root, can't you replace the 9 minus 3 sine theta squared with 3 cosine theta squared?
All right, so this guy is our really useful one. That 9 minus 3 sine theta quantity squared, the reason that we wanted to do this trig substitution is that this part under the square root, we can replace it with one term squared. So we've got the integral of 1 over 3 sine of theta squared, and we've got the square root of, instead of 9 minus 3 sine theta squared, we end up with 3 cosine theta quantity squared, and then 3 cosine of theta d theta. And we really like that a lot, because what that does for us is this square root and that square right there, bam, they cancel each other. And so we are left with the integral of 1 over 3 sine of theta squared times 3 cosine of theta, and then in our numerator again, 3 cosine theta d theta. All right, so our goal here was to get rid of that awful square root. And the way that we can do it is that we can do this clever and rather tricky trig substitution that said, if we can manipulate and morph this guy, the 9 minus x squared, turn it into something that is a trig identity, replace that with a single term, then we can clean up that square root. Okay, so now we've gotten rid of that square root. And so we look at this integral again, and we still have thetas all over the place. Anything we can do to clean this up?
Cancel.
Yeah, we can cancel. We can cancel our cosine of theta. We can cancel 3. And that leaves us with the integral of 1 over 3 sine of theta quantity squared d theta. All right, are there any questions about that? Okay. So our integral is getting better. We now have 1 over 3 sine of theta quantity squared. I'm going to go ahead and expand. In other words, I'm going to distribute that square sign. So I have 1 over 9 sine squared theta d theta. And I can pull that 1/9 out in front. And I have the integral of 1 over sine squared theta d theta. All right. So now the question is, what's our antiderivative? I don't know an antiderivative for a sine squared, and besides that, it's in the denominator.
Theta plus 1.
What's that?
It's the same as, here, sorry.
So 1 over sine is the same as cosecant. So you could write this as cosecant squared theta d theta. Anybody know an antiderivative for cosecant squared?
And it, cosecant times.
Minus cotangent?
Yeah, so if this were secant squared, then your antiderivative would be positive tangent. So with the cos, just put the co in front and toss a negative in there. And so this becomes 1/9 times negative cotangent of theta plus c. Alright, so we now have negative 1/9 cotangent of theta plus c. We have an antiderivative, and we're pretty happy because we've gotten rid of all the integral signs, we've gotten rid of the square roots, and life is 95% good. Alright, now, I say 95% good because we're not quite done. Our original integral, in terms of x's. Our final answer right here is in terms of theta. So it's not really our final answer. We now need to reintroduce our x's. So what you might remember is that x was equal to 3 times the sine of theta. Hopefully you have that boxed off on your paper. And so the question is, what are we going to do with this expression up here? And the answer is, I really need to know my trig well at this point. Okay? Because I have x equals 3 times the sine of theta. If I solve for sine of theta, I get x over 3. In terms of right triangles with opposite, adjacent, and hypotenuse, sine of theta is what ratio?
This over hypotenuse?
So
Yeah.
opposite over hypotenuse.
Yeah, it's opposite over hypotenuse. So if I draw a triangle, a right triangle here, with an angle of theta, my opposite side is x, my hypotenuse is 3. Now what we'd like is to figure out what cotangent of theta is equal to. Now, cotangent of theta,
Adjacent over hypotenuse.
well, so cotangent is the reciprocal of tangent. Tangent is opposite over adjacent. So adjacent over opposite.
Oh yeah. So cut.
Alright, so cotangent is adjacent over hypotenuse. We know the hypotenuse, but we need the adjacent side. We need to figure out that third side here. Pythagorean theorem. Alright, so what do we have? We have x squared plus, let's call that a, plus a squared equals 3 squared. And you thought you'd never need your trig again. Alright, so that means that a squared is equal to 9 minus x squared. And so a is equal to the square root of 9 minus x squared. No, that would be illegal algebra to split up the square root over the negative over the minus sign. Only over multiplications. It's allowed in multiplication, but not subtraction. Okay. So now we've got our cotangent. So that tells us that cotangent of theta is equal to adjacent, square root of 9 minus x squared, over opposite, which is x. Okay. Our negative 1/9 times the cotangent of theta now becomes so negative 1/9 cotangent of theta plus c is negative 1/9 times the square root of 9 minus x squared over x plus c, and this is our final answer. All right, so that was a bold problem, okay? A lot of stuff that went into it. Let's summarize this and then we'll take our 10-minute break. So we had the form where the square root of x squared, or a squared minus x squared, showed up in the problem. We identified this with 1 minus sine squared theta is equal to cosine squared theta. We said that the number minus the x squared kind of looks like the number minus sine squared. The substitution that we made was we said let x be equal to a times the sine of theta. In our case, x was equal to 3 sine theta. And our result was that we ended up with the square root of a squared minus x squared being equal to a times the cosine of theta. That was where we made that cancellation. We took a squared minus, or we took 9 minus 3 sine of theta squared and replaced it with a cosine theta. So these are the pieces that went into all of that work. You have an option. You can either memorize this first row of the table, or you can think through what we did on that first problem. Either way, I mean, you know, you get to a test and you say, and all the table gets all jumbled in your head, then you want to be able to logically go through it as well. Okay, so please take a 10-minute break, and when you come back, we're going to look at 2 more examples.